Hey everyone, welcome to this explainer. Today we are going to fundamentally change how you look at data, news headlines, and those really complex policy decisions. We're diving deep into the fascinating world of causal inference and causal thinking. If you've ever looked at a shocking statistic online and thought, wait, does that really cause that? Well, you are definitely in the right place.
Here is our quick roadmap for today. We'll start with the correlation trap, move on to enter causal inference, dig into hidden variables and biases, unpack the causal toolkit, and finally, look at real-world causal thinking. Let's get right to it.
Section 1. The correlation trap. You know, to really grasp causality, we first have to confront a pretty massive flaw in human intuition. Let me ask you kind of an absurd question. Does eating ice cream cause crime? Seriously, imagine you're looking at city data, and you see this crystal clear trend. As ice cream sales spike, violent crime rates also go right up. When sales drop, crime drops. If you just take those numbers at face value, you might actually think sweet treats are fueling a literal crime wave.
But obviously, that's not what's happening. What's really going on here is a sneaky third factor at play. It's not the ice cream driving the crime, it's the summer heat. High temperatures cause both a spike in ice cream sales and more people being outdoors, which unfortunately leads to more conflicts. The two variables totally move together, but one absolutely does not cause the other.
And that brilliantly illustrates our first major takeaway, the crucial difference between correlation and causation. Correlation just measures how much variables are related, meaning they tend to change together, right? Just like the ice cream and the crime. Causation, though, that implies a change in one variable directly forces or leads to a change in the other. It is the literal difference between a total coincidence and a direct mechanism.
Section 2. Enter causal inference. So if we literally can't trust our own eyes when we see two things moving together, if simple correlation is a trap, how do we actually find the truth in the data?
Well, enter causal inference. Think of this as our hero. It's a rigorous scientific and statistical method entirely dedicated to figuring out the actual cause and effect relationship between variables. It's the mathematical framework we use to stop guessing and start mathematically proving what actually leads to what.
Because, unlike mere correlation, causal inference explicitly seeks to establish if a change in one variable directly leads to a change in another. It's not about two things just being associated in a spreadsheet. It's about intervention and direct, measurable impact.
Moving on to Section 3, hidden variables and biases. Proving causality means we've got to jump over some incredibly tricky statistical hurdles. To get to the absolute truth, data scientists have to battle three main villains that love to skew our view of causal relationships: confounding variables, selection bias, and measurement error. Let's zoom in on the most dangerous traps here.
Okay, first up, we absolutely have to recognize confounding variables. A confounder is basically a hidden variable that affects both the supposed cause and the supposed effect, creating a totally fake correlation. This is exactly like the hot temperature in our ice cream and crime example, right? The temperature was the confounder secretly pulling the strings from the shadows, making it super difficult to isolate the true relationship without really careful statistical control.
Another massive trap is selection bias. This happens when the sorting of individuals into a program or a treatment group isn't random at all. Like, let's say you're testing a brand new job training program and only the absolute most motivated people sign up for it. Your results are going to look amazing, but wait, is the program actually that good, or did you just select people who are going to succeed anyway? That kind of unfair sorting totally ruins the accuracy of our estimated causal effect.
Section 4. The Causal Toolkit. Now that we know the traps, let's equip ourselves with the actual tools researchers use to defeat them.
The absolute gold standard for proving cause is setting up a rigorous comparison. We take our subjects and divide them into two distinct groups. The treatment group gets the intervention, say a new medicine or a new educational policy. The control group, they just do what they normally do, no treatment. By contrasting these two groups, researchers can completely isolate the exact variable they're testing while holding everything else constant.
By looking at the treatment and the outcome, the ultimate goal is to measure the causal effect. And the causal effect is just the difference in the outcome between your treatment group and your control group, assuming you've successfully held everything else constant. That difference? That is your pure, undeniable proof of cause.
Mastering these specific statistical concepts, like treatments, controls, and confounders, actually unlocks a much broader, incredibly powerful mindset. We call it causal thinking. It's the process of deliberately understanding how one event leads to another so we can make sense of a really complex world, rather than just jumping to lazy assumptions.
Which leads us perfectly to Section 5, Real-World Causal Thinking. Let's step out of the textbook definitions for a second and talk about why this actually matters for society, for public policy, and honestly, for you.
Applying this framework is absolutely vital, especially in areas like development and public policy. Governments have to use causal inference to enact evidence-based decisions. For instance, did a new literacy program actually cause an increase in graduation rates, or was it just a broader demographic trend? We have to know. In business, it helps leaders find the true root causes of problems instead of just slapping a Band-Aid on symptoms. And on a personal level, it literally stops you from being fooled by bad data and biased news.
Because it establishes absolute truth rather than just loose association, causal inference is the rigorous foundation across so many crucial fields. In medicine, it proves if a drug actually cures a disease. In economics and the social sciences, it proves if a social program actually lifts people out of poverty. It is the unquestionable gold standard for measuring real-world impact.
Our modern society depends heavily on making these distinctions. Whether scientists are identifying the exact causal impact of human activities on climate change to inform global policies, or educators are measuring how different teaching methods actually impact student outcomes, we rely entirely on causal models to find solutions that work in reality.
So as we wrap up this explainer, I really want to leave you with a final thought. The next time you're reading an article or someone pitches you a super compelling data trend, take a step back. Ask yourself, am I looking at a true cause here, or is this just a coincidence? Are there hidden confounding variables lurking in the background? I hope you're leaving today as a much smarter, more critical consumer of data, ready to push past the mere correlation and demand the true cause. Thanks for joining me.